Okay, so welcome to part 2 of our question. Is it possible to predict the pH behavior of oxides? We established in the previous video that oxides are very common, so it's a good question to ask ourselves. How can I predict their behavior in terms of pH? Now, it may surprise you to know that most oxides, metallic oxides, are actually insoluble in water. This is probably a good thing because, as I argued in the last video, they're very common in the Earth's crust. If they were particularly soluble, well, they would soon dissolve into water and much of the Earth's structure could well end up dissolving as well. We used magnesium as our example, and you'll remember that magnesium sits around here in the periodic table, and it's a metal, which means because of the structure of the periodic table, magnesium is a good case study for any metal which will probably behave very similarly. Now, magnesium itself as an oxide looks a little bit like this, but as I just argued, oxides don't tend to dissolve. Group 1 oxides will, the guys that live over here, and some other exceptions, but for the most part, metallic oxides are insoluble. So if we wish to determine their effect on the pH of a solution, we can't simply put them in water because they won't dissolve in the water and so pH will be unaffected. However, chemists discovered over time that these oxides, metallic oxides, do affect pH in different circumstances other than just dissolving in water, and so we wished to understand it. What we need to do, therefore, is apply some different tests. If I can't dissolve it in water, I wonder if magnesium oxide could be dissolved in anything else. It turns out it can. Chemists discovered that metallic oxides tend to react with acids in a certain way. If you put your metallic oxide into an acid that's concentrated enough, we seem to get some interesting reactions. What tended to happen was that magnesium oxide would form a salt. In this instance, because it's hydrochloric acid, you would get magnesium chloride, and it produced something else. I wonder if you can guess. A hydrogen was left from the acid, and oxygen was left from the oxide. Of course, it's not hard to see that we're going to form some H2O. That would have a liquid form. Of course, we want to balance things because we are chemists. One hydrogen was on the left, but now there's 2 on the right, so I must have had 2 lots of hydrogen on the left, and that fixes the problem where we see that 2 chlorines on the left are now accounted for in terms of chlorine on the right. So this is what started to happen. Different metallic oxides will behave in exactly the same way, and so it was established that in this instance, magnesium oxide tended to behave as what we would call a base. I don't know if you can remember from junior science, but you would have been introduced to a certain law in chemistry. An acid plus a base gives salt and water. Here we know that we have an acid, hydrochloric. If it reacts with this compound, then we can confirm that this compound, magnesium oxide, must be acting as a base, because without a base, you couldn't possibly get a new salt and water. So this is our chemical proof for the behavior of a metallic oxide as a base. So now we have a rule. Metallic oxides tend to be basic, and you can choose any of them, and if you're asked to predict how it would affect the pH of a solution, you can now successfully show via neutralization that because it's able to neutralize an acid, it must be acting as a base. Now, that rule stands, however, like all good chemistry rules, there are some exceptions. Now, these exceptions are a couple of elements that you'll need to be aware of. The elements in question are elements that sit around this sort of area of the periodic table. This area here should really be coloured in a little bit more carefully as red as well to indicate this is a part of the metallic part of the periodic table. But we're starting to see that there are some exceptions to the rule, and those exceptions to the rule are all involving metals that live around this area of the periodic table here. This area of the periodic table is very close to this line which sort of differentiates and separates elements on the periodic table that are different. You're probably aware of the fact that down this area you have what we would call semi-metals. They're elements that seem to be a little bit like metal and a little bit like non-metal. And then in this area of the periodic table, of course, we have what's called the non-metals. But what about elements that aren't quite semi-metals, but live very close to the line? They sort of live on the edge, if you like. Well, we would expect that the closer we get to this division line in the periodic table, the closer these elements are to behaving maybe a little bit more like non-metals. And that's true of 4 very important metals: zinc, aluminium, lead, and tin, all of which you find down in this area of the periodic table, actually break the metal oxide rule. Remember, what was our metal oxide rule? That metallic oxides all tend to behave as bases in solution. So here's zinc oxide, here's aluminium oxide. If you want to know why aluminium oxide looks like Al2O3, watch one of my other videos on balancing. Here is lead oxide. We'll use the common valency of 2+ there, which makes for easy balancing. And tin oxide will do the same, SNO. Now, we've already established that these would be common forms of these metals. Oxygen is everywhere, so they tend to react with oxygen and form an ionic metallic oxide. Now, according to the last video, we would predict that zinc oxide, aluminium oxide, lead oxide, and tin oxide would be basic oxides, purely because they are metallic oxides, and we established a law using magnesium as an example that metallic oxides can neutralize an acid. This is not true. What we have here are examples of what we call amphoteric oxides. And to understand amphoteric oxides, I want you to imagine a little frog. Now, this is my drawing of a frog. It's not particularly good, but it's kind of cute. Now, if you think of the word amphibian, that amph seems to suggest something about what frogs can do. An amphibian can live on the land and in the water. It can do both. Well, an amphoteric oxide can actually behave in 2 ways. It's not a frog living on the land and in the sea, but an amphoteric oxide can actually behave as an acid or a base. Now, our 4 amphoteric oxides that you need to be quite familiar with, and some other metals can sometimes display amphoterism, but these are the 4 classic ones: zinc oxide, aluminium oxide, lead oxide, and tin oxide are all amphoteric, meaning they can act as bases if there's a lot of acid around, or they can act as acids if there's a lot of bases around, which means these guys, zinc oxide is capable of neutralizing an acid, whereas zinc oxide is also capable of neutralizing a base. It can do both. It is amphoteric. How on earth can I remember these metals? Well, I always like to have little songs to help me remember exceptions to chemical rules, so I'd like to give you one of my memory tools now to help you remember this, and I'm going to draw a little note here to indicate that we have a song to remind us of these 4. And what I do with my students is we simply sing this little song to remind ourselves. We say zinc, aluminium, lead, and tin, amphoteric oxides don't fit in. In other words, they don't fit the rule. They don't fit into what every other metal does in terms of affecting pH. They are different. They are amphoteric. They don't fit the rule. They can actually do both. Zinc, aluminium, lead, and tin, amphoteric oxides don't fit in. If you remember that little song or rhyme, you'll remember that these are exceptions to the rule, and your prediction, if asked about their oxides, would be that unlike other metallic oxides, these 4 can turn into oxides that affect pH as both a base and or an acid, depending on the pH of the surrounding solution.